I'm going to go through the answers to exercise 2 on page 23. The first question asks you to write the electron configuration using shorthand. So for magnesium, using the shortcut, I go to the period above magnesium, which is period 2, and I write down neon. Magnesium has an extra 2 electrons, so it's going to be 3s2. For vanadium, the noble gas above vanadium is argon. After argon, you have another 1, 2, 3, 4, 5 electrons to assign for vanadium, and they fill into the 4s2, and then you got 3d3. For cobalt, after argon, you've got another 9 electrons to assign. You're going to put 2 electrons in the 4s orbital, giving you 4s2, and then 7 into 3d. For copper, you've got another 11 electrons to assign. Rather than having a 9-2 split as expected, you get 10 electrons in the 3d orbital, 1 electron in the 4s orbital. The next one's a chlorine ion, so it's chlorine but with an extra electron. The noble gas in the period above chlorine is neon, and then you're going to have 3s2 and 3p6. Because it's gained an extra electron, it now has a full outer shell. 2 and 6 is 8 electrons. Aluminium has lost 3 electrons. When it loses 3, it has the same configuration as neon. Zinc has lost 2 electrons. So zinc normally, if we see it over here, would have a full 3d orbital. When it loses 2 electrons, it doesn't lose any from the 3d orbital, it loses them from the 4s. So the 3d stays full, 3d10, but you lose the 2 electrons in the 4s orbital. For all of these, at the end, do yourself a quick check, count the number of electrons that you have got, make sure it matches the atomic number on the atom in question. The next question, you're asked to draw dot and cross diagrams. You're only using the outer shell electrons. I have not drawn circles, I haven't actually drawn shells. You don't need to draw shells, you just need to show the electrons that will be in those shells. So for calcium, as I'm drawing it after losing 2 electrons, I have drawn no electrons around calcium at all. Sulfur, I'm drawing it with its 6 own electrons using dots, and I'm drawing it with 2 extra electrons, which it got from calcium. Calcium is 2+, sulfur is 2-. The next one, potassium oxide. Okay, potassium's in group 1, it will lose 1 electron to give a +1 charge. Oxygen's in group 6, so it's got its own 6 electrons and it needs to gain 2. Because it needs to gain 2, you need 2 potassiums. So each potassium will have a +1 charge. The oxygen will have a 2- charge from the 2 electrons it's gaining. MgCl2, okay, so I'm drawing magnesium with no outer shell electrons and a 2+ charge. I'm drawing chlorine with its 7 own electrons and 1 extra electron that would have gotten from magnesium. Each chlorine has a -1 charge. From aluminium nitride, aluminium wants to lose 3 electrons, so it's +3. Nitrogen, I've drawn its 5 of its own electrons. It's 3 extra electrons from aluminium. It's got a -3 charge. The last example, aluminium bromide. Aluminium needs to lose 3 electrons, therefore it needs 3 bromines that will each take 1 electron. Each bromine is drawn with its 7 own electrons and 1 extra electron that it got from aluminium. Aluminium has a +3 charge, each bromine has a -1 charge. In all of the above examples, you will see that the number of positive charges and the number of negative charges are the same, so they should always balance. In question 3, you're asked to write the formula for the following ionic compounds. So sodium sulfide, I've written it as Na2S. That's because sodium is in group 1 and it would have a +1 charge. Sulfur is in group 6, it would have a -2 charge. So you need 2 sodiums to balance out the charge on sulfur. So sodium will be, there we go, +1. Sulfur will be -2. I need 2 sodiums to cancel out the 2 negative charges on sulfur, giving me Na2S. Cesium bromide. Cesium's in group 1, so it's +1. Bromine's in group 7, it's -1. +1 and -1 cancel out, so just CsBr. Magnesium nitride. Magnesium's in group 2, it would have a +2 charge. Nitrogen's in group 5, it would have a -3 charge. To get these charges to cancel out, I would need 3 magnesiums, giving me +6 in total. 2 nitrogens gives me -6 in total. My charges are cancelling. Chromium 3 oxide. Chromium is one of our transition metals. I can't just look at the periodic table and see its charge, so I need to look at what's in Roman numerals. I've got 3 in Roman numerals, okay? Chromium's a metal, so it's always going to be positive, and the fact that it's followed by a 3 tells me it's going to be plus 3. That means chromium has got a plus 3 charge, and I know oxygen is always minus 2 because it's in group 6. In order to get these charges to cancel, I will need 2 chromiums to give me a total of plus 6. I will need 3 oxygens to give me a total of minus 6. So I get Cr2O3. Tin chloride, again, it's another transition metal. Tin is followed by 2 in Roman numerals. That tells me that tin is plus 2. Chlorine is only minus 1, so I need 2 chlorines to balance out the 2 positive charges on tin, giving me SnCl2. Nickel 2 selenide, okay, so nickel, again, it's followed by 2 in Roman numerals. That tells me nickel is plus 2. Selenium is in group 6 under sulfur. It's in group 6, it's got a minus 2 charge, plus 2 minus 2, they cancel out, NiSe. Aluminium oxide, okay, aluminium is in group 3, it's got a plus 3 charge. Oxygen is in group 6 with a minus 2 charge. 2 aluminiums will give me a total of plus 6. 3 oxygens will give me a total of minus 6. Copper 1 iodide. Copper 1 will have a plus 1 charge. Metals are always positive. Iodine's in group 7 with a minus 1 charge. They cancel out and you just get CuI. In question 4, you're asked, what is an ionic bond? There is only one correct answer. Okay, you have to mention the electrostatic force, and you have to say it's between oppositely charged ions. If you said it was the bond that forms between a metal and a non-metal, you will not get any marks. If you describe how an ionic bond forms, if you talk about electrons being transferred from a metal to a non-metal, you also will not get any marks. You have to state electrostatic force between oppositely charged ions. A giant ionic lattice, you have to have this phrase, a repeating pattern of oppositely charged ions held together by the electrostatic force of attraction. It would be a 2-mark question, and what's commonly forgotten is this phrase, a repeating pattern. What type of structure does aluminium chloride have? Okay, you need to recognize that aluminium chloride, aluminium is a metal, chlorine is a non-metal. So if you've got a metal and a non-metal, it's going to be ionic. All ionic compounds have a giant ionic lattice structure. What state will aluminium chloride be at room temperature? We know aluminium chloride is ionic. If it's ionic, then it is going to be solid at room temperature. And the reason is because aluminium chloride is made up of oppositely charged ions. There is a very strong electrostatic force between these oppositely charged ions. If you've got a really strong attraction between the particles will be held tightly together. And if they're held tightly together, you're going to have a solid, okay? Also mention the other key phrases, okay? It's in a giant ionic lattice. And anytime you're talking about what state something will be, or you're talking about melting point, you should always talk about energy. Because the bonds between the ions are so strong, a lot of energy will be required to break those ions apart. And at room temperature, which is typically around 23 degrees Celsius, there's just not enough heat energy at room temperature to supply the necessary energy to separate those ions when they're so strongly held together. The next one, you've got sodium chloride and you've got magnesium oxide, and you've got 2 different melting points, okay? They're both ionic compounds. You've got a metal and a non-metal here, and you've got magnesium a metal, oxygen a non-metal. But there's a big difference in their melting points, okay? The first point I'm going to make is that magnesium oxide is a higher melting point. That straight away tells me that magnesium oxide must have stronger bonds. But I now need to go on to explain why the attraction between the ions of magnesium is stronger than the attraction between the ions in sodium chloride. If I look at the charges on the ions, okay, if we look at the magnesium and oxygen ions, magnesium's in group 2, it's got a charge of plus 2. Oxygen's in group 6, it's got a charge of minus 2. Compare that to sodium chloride. Sodium in group 1 has a charge of plus 1. Chlorine's in group 7, a charge of minus 1. So in magnesium oxide, you've got ions with plus 2 and minus 2. These charges are higher than the charges we see in sodium chloride, where you've got plus 1 and minus 1. Okay? The higher the charges on the ions, the stronger the attraction between the ions. I need to write that as a comparative sentence. So I need to say that the charges on magnesium and oxygen are higher than on the charges of sodium and chloride. And then I need to specify that the higher the charge, the stronger the force between the ions. The stronger the force, the more energy required to overcome, and therefore they have a higher melting point. Why can sodium chloride conduct electricity in solution but not as a solid? We've talked about when conducting electricity, those ions have to be free to move. Okay? In a solid, the particles, the ions, cannot move freely. They're held in fixed positions and can only vibrate. in solution, those ions can move freely. So I'm going to say in solution, the ions are mobile. That means they can carry current. As a solid, those ions are not mobile. They cannot carry current. You need to mention that word ions in your answer. You can't just say particles, and you definitely cannot say delocalized electrons. The particle you're talking about are ions. You need to explain that. And the last one, why does sodium chloride dissolve in water but not in hexane? We said in order for something to dissolve that there needs to be a strong attraction between that ionic compound and the solvent that they are dissolving in. So I've got sodium chloride. It is dissolving in water. If it's dissolving in water, that tells me that there's a strong attraction between the sodium and the chloride ions and the water molecules themselves. Okay, that attraction is so strong between the water and the ions that it can overcome the attraction that exists between the ions themselves and actually pull those ions apart. It says it doesn't dissolve in hexane. That tells me that the attraction between ions and the hexane molecules is not very strong, and it is not strong enough to overcome the force that holds the ions together. Okay, so it will dissolve in water. It will not dissolve in hexane.